Streams are valuable features of the landscape that provide water for drinking, transportation, energy, manufacturing, and wastewater treatment. Homes, factories, and water supply systems built along streams have easy access to its services, but are also vulnerable to flooding, and vulnerable to the constantly changing path and shape of the stream channel. The stream in this demonstration has evolved from a straight channel to one with curves, or meanders, that move back and forth across the landscape. During high flow, the stream overtops its banks and spreads out on a floodplain, visible when the floodwaters recede. To protect our built resources, people often try to control the path and shape of a stream by armoring or hardening the banks of the stream. Armoring may be accomplished by installing very large stones, concrete blocks, wire baskets of boulders, or by paving the sides and bottom of the stream with concrete. Here, the outside bank of a meander has been armored to protect that side of the stream from the erosion that occurs on the outside bank. As a result, there is a change in the erosion and deposition happening up and downstream of the armored segment. Note that the stream channel along the armoring has deepened. Also, stream bank erosion is starting to occur just upstream of the armoring on the outside bank. Water is being deflected from the armored bank across to the inside bank, causing increased erosion on the inside bank. While the inside bank is usually armored only in conjunction with armoring of the outside bank, we show this scenario to illustrate further the impacts of armoring. Again, notice the difference in the erosion and deposition occurring up and downstream. We see that the moving water is deflected from the armored section across the channel to the non-armored opposite bank. Erosion occurs on the opposite bank, widening it. In both cases, the path of the channel is shifted by the changes to the stream bank in response to the moving water. Another stream modification, the model culvert in this stream, has also changed the stream flow. The culvert creates a constriction or narrowing of the stream. Where does the kinetic energy in the force of the moving water go in this case? To move the same volume of water through this constriction, this smaller cross-section, the water must flow faster. This faster flowing water now picks up sediment at the mouth of the culvert, digging out a depression. This creates a small elevation drop in the stream channel, which in turn increases the stored energy or head of the stream at that point. As time goes on, the increased head causes more erosion, and the front of erosion moves upstream. This effect, as counterintuitive as it is, can be seen here. In addition, eddying around the edges of the culvert can cause erosion outside of the culvert. As water leaves the culvert flowing fast, its higher velocity gives it the energy to erode the stream channel at the outlet of the culvert, sometimes creating a pool. Further downstream, the water again slows down and drops its load of sediment downstream of the culvert. During storms, there may be so much water moving through the stream channel that the water is also forced to flow over and around the culvert. With a large enough storm, there may be enough stream energy to actually move the culvert. We have seen that streams change over time in response to changes in the energy of the stream, due to the amount of water flowing in the stream channel or to physical restrictions on the stream, such as adding a culvert. The energy of the stream and how its energy is dissipated is the cause of changes to its shape and path.